So let's take a look at a few worked examples. I'm keeping my voice down because he's sleeping. So let's return to the airboat. Who doesn't love airboats? And here we have an airboat with a total mass of 3.5 times 10 to the 2 kilograms. He's driving in a straight line for 50 meters. The airboat's engine gives us a horizontal force of 7.7 times 10 to the 2 newtons. What's the value of the acceleration of the airboat is our first question. Part B says how long will it take the boat to reach 12 meters per second, and C, what's the resistance force due to the water after the engine is switched off if the boat stops in 50 meters. Now you may have seen questions like these before, and in some ways I want to point these out because you can use interchangeably things like energy or kinematics based on what you're given, and usually it's a sort of judicious choice as to which is simpler. So here's our displacement of 50 meters, here's our force of 7.7 times 10 to the 2 newtons, and here's our resistance force. So writing down what we've got, here's our mass, here's our force, here's our acceleration, and here's our displacement. So for part A, let's engage with F equals ma. There's no reason to go back to all your kinematic equations and select them out and figure out S and A and everything else if you've got a basic equation that you can use. We have a force, so here we can safely employ F equals ma. A simple rearrangement will give us A equals F over m. I've dropped my units, please don't do that, but 7.7 times 10 to the 2 over 3.5 times 10 to the 2 will give us 2.2 meters per second as an acceleration. The negative 2 is off the slide here. Part B asked us what was the time to reach 12 meters per second. Well, we have an acceleration now, and we're armed with a time. Now we can return to our equation of motion, of course, which will allow us to reinvent the simple idea of acceleration being a rate and t being the time that that rate is applied. So v equals vi plus at will give us 0 for our initial velocity plus 2.2 meters per second times t. So t will be 12 over 2.2, which will give us 5.45 seconds. Now part C asked for the resistance force with no engine. So the engine is switched off, and eventually, without the engine being switched on, of course, the boat will come to a stop. What we really need here is a force. We know the mass of the boat, so we need to engage with an acceleration. This means we can use Vf squared equals Vi squared plus 2as, stepping back into kinematics once again. This means Vf squared minus Vi squared is equal to 2as. Now we have a final velocity of 0 and an initial velocity of 12. This is equal to 2 times a times 50. A rearrangement will give you an a of 1.44 meters per second. An acceleration to the left though, a negative acceleration slowing the boat down, what you'd in civil terms call a deceleration. Now using F equals ma, we can now apply our mass, and we'll find if we multiply our mass by negative 1.44 meters per second, we'll end up with negative 504 newtons of force, bringing the boat to a stop. Shifting gears back to work and power. We now have a horizontal cable that's moving a package. We have a frictionless surface, unrealistic, but simplifies our problem. And the work is done by the cable's force. So here's a package with a cable attached, and it's going to pull our package along. And the work is given by this function. Work is equal to 0.2 joule per second squared t squared. What is the average power due to the force provided by the cable at t equals 10 seconds? So our mu is equal to 0, no friction, and a force is provided by the cable pulling the package along. We want the average power from what we have functioning work at 10 seconds. So the work done comes from this function. We want the power. Well, we're going from T1 being 0 seconds to T2, which is 10 seconds. So we can simply substitute in to our expression. We don't need to do much else. So our initial work is at T equals 0. If we substitute in, we'll amazingly get 0 joules. Substituting in for the second point, this will be 0.2 joules per second squared times 10 squared here, which will give us 20 joules. So this is the work done. This is not the power. Now, typically, if a question like this is set on an exam, people get very excited that they've managed to solve this so simply by realizing this trick, and then they forget to do this last part. That work is done over 10 seconds. So the power here is 20 joules over 10 seconds, which gives us 2 watts or 2 joules per second. So here we have a mass that's lying again on a frictionless floor, a mu equals 0 floor, and is attached to the end of a spring. So, as shown here. We now have an applied force of 4.9 newtons that's needed to hold this block steady. So imagine a hand from the previous lecture. The mass is stationary at 12 millimeters. At delta x of 12 millimeters. So, we have a question here. How much work does the spring force need to do on the mass if the mass is pulled from a position of 0 here to an x position of 17 millimeters? And part B, the mass is then moved left from 17 millimeters, the point we're looking at for x3, to a compression of negative 12. So in part 1, we're going from 0 here to 17 millimeters. In part B, we're going from 17 millimeters over here to negative 12 millimeters. How much work does the spring force do on the mass during that displacement? And we'll talk about the sign that's applied to the work. So there's our variables, mass on a frictionless floor, force is 4.9, to hold it stationary, that's you have to apply a 4.9 Newton force to make sure the block does not move and the spring does not pull it. We've got an x, which is 12 millimeters for part A, which is 12 times 10 to the minus 3 meters. We have to convert this to meters because we have to look at the spring in terms of newtons. So the work done, if we go from x equals 0 to x equals 3, this is 17 millimeters, and we'll work to hold it steady at 12 millimeters. So we can say here F is equal to negative kx. K is the force on the spring over x2. What we're saying for K is this is going to be 4.9 newtons over 12 times 10 to the minus 3 meters, giving us 408 newtons per meter. So we've figured out what K is. In moving this spring 12 millimeters, we've figured out the force per meter that we need. So this is the spring constant in F equals Kx. We had X, we had F, we figured out K. Now, for the X equals 17 millimeter case, since we have K, we can now say the work done by the spring is going to be our half Kx squared. This is a 408 newtons per meter times 17 millimeters, 17 times 10 to the minus 3, which will give us 0.0589 or about 0.06 joules. Now part B saw the block being displaced in different directions. If the block is now moved to the left, so we're still at x equals 17 millimeters as per the previous problem, but then it's moving to -12. So it's passing its 0 point and the spring is being compressed. What's the work done by the spring's force? Well, both positions, remember, are with respect to the equilibrium, not the total displacement. So the work done by the spring can be found by the difference in those two positions of the spring, two extensions of the spring. So the work done by the spring will be half kx squared for one position minus half kx squared for the other position, or 1/2 k x3 squared minus x4 squared. This will give us 408, 1/2 408 times 17 times 10 to the minus 3 squared minus 12 times 10 to the minus 3 squared, which will give us 0.03 joules, or 30 millijoules. So we looked at a question like this during the slides, but let's take another look. Here we have a man in a weightlifting competition. He's lifting a weight of total mass 260 kilograms, a height of 2 meters, where he holds it stationary above his head. He's probably quite a short guy. Part A says, during the lift, how much work was done on the weight by the gravitational force. Part B says how much work was done on the weight by the man's applied force, and Part C wants to know how much work is done on the weight while he's holding it stationary above his head. One of these should be immediately obvious without a formula, by the way. So Part A with an extra question mark added just for extra inquisitiveness. The weightlifter is lifting a mass of 260 kilograms through a displacement of 2 meters. So the work done by gravity here is Fs. We'll use negative mg times delta y, which will give us minus 2,548 newtons times 2 meters, which will give us minus 5,100 joules. Part B states how much work was done on the mass by the man's applied force during the lift. Well, the force likely wasn't constant, but we can't really take that into account. So the objects were stationary at the beginning and end of the lift. So we can say K2 minus K1 was equal to 0. Or, from our work-energy relation, we can look at the applied force. The applied force by the man, essentially, will be opposite to the work done by the applied force due to gravity. If we look at work equals F times S, then the work done by the man should be the opposite of that done by gravity, which will be essentially 5,100 joules. So, how much work did the man do? Well, if the work done by gravity was negative, the work done by the man will be positive 5,100 joules. And part C, how much work is done on the mass while he's holding it stationary above his head? Altogether now, work is force times displacement. If he's holding it stationary, he's going to do 0. V is 0, S is 0, work is 0. Finally, let's take a 2.5 kilogram bowling ball and smash it into a wall at 6 meters per second. During that reaction, the ball is going to come to rest. So there's our 6 meters per second, a ball hits the wall, it comes to a stop of 0 meters per second. Now, how much work was done by the wall in bringing the object to 0, to a velocity of 0? Our mass is 2.5 kilograms. The initial velocity was 6 meters per second. The final velocity was 0 meters per second. And this is one of those questions that people often get involved in with an equation of motion and try desperately to find an acceleration and therefore find a force and then find the work done from work equals force times displacement. that wouldn't be the way to go here. You don't have a displacement. You don't have an acceleration. What you do have is velocities and masses. So here, the smart way to go is to say my work is a change in kinetic energy. I'm going to start with a half mv squared at 6 meters per second and go to a half mv squared of 0 meters per second. This gives me 1/2 2.5 times 6, as our second answer is 0, squared. So 1/2 2.5 times 6 squared will give us 45 joules of work done to bring the ball to rest. Now if the ball comes to rest in 0.4 seconds, how much power was used to stop the ball? This one should be relatively simple. Power, of course, is defined as work over time. We have 45 joules of energy and 0.4 seconds, which gives us 112.5 watts.